Okay, welcome to day 1 of Unit 2 of Pre-Cal. We're going to be studying polynomial functions this unit, and this is going to take place in Chapter 4 of the textbook. Okay, so a polynomial function is a function of the form f of x equals a sub n times x to the nth power plus a sub n minus 1 times x to the n minus 1 power plus a sub n minus 2 times x squared plus, we continue on this pattern till we get to plus a sub 1 times x to the first power plus a sub 0 times x to the 0 power. And keep in mind, x to the 0 just equals 1, so there really is no x in this last term. It's a constant. This is where x is a variable and a's are real numbers, and n is a non-negative integer. So it can't be a fraction there. The degree of a polynomial function is the largest power of x. So typically we write these in order. That's the proper form. So the highest exponent first, going to lowest exponents of the x. The domain then is going to be the set of all real numbers and we could write that, our fancy r, we could write it as negative infinity to positive infinity, or we could use the inequality notation of negative infinity is less than x, which is less than positive infinity. But it's the domain for all our polynomials will be all real numbers. Okay, and now we want to take a look at these 6 and decide if they are polynomials or not. So are they of the form listed above? So notice on function a, first of all, it's not in proper form, that we've got the largest exponent last. It doesn't change the value of this, but when we're looking for our degree, we have to look for the largest exponent. So first of all, yes, this is a polynomial function, and the degree, so degree equals 8, the largest exponent of x. On function b, notice I have an x in the denominator. This tells me this is a quotient, which is not a polynomial function. So no, it is not a polynomial function. It is a function, just not polynomial. C, there's no x in here. But remember up here, we said x to the 0 is the same thing as 1. So this is really 5 times x to the 0. That's a polynomial. So yes. And our degree is 0. Okay, coming down over here. So f of x is x minus 3 times x plus 2. Well, we really need to multiply this out to see what we have. So we're going to just do FOIL. So x squared plus 2x minus 3x minus 6, which gives us x squared minus x minus 6 when I combine those like terms. So yes, that looks like a polynomial, and my degree is 2. That's the highest exponent that we have. Okay, part E, my function is 3x minus 4x to the negative 1. Well, again, remember we said n is a non-negative integer. That's a negative integer, so no. And it's due to the negative exponent right here, that it is not a polynomial function. Okay, and F, last example here. I've got a lot of fractions as my coefficients, so these would be like a sub 3, a sub 2, a sub 1. That's perfectly okay that they're fractions. The exponents are all positive integers, so we're good, yes. And the degree, again, look for the largest exponent. So my degree is 3 in this example. Okay. Okay, let's continue on here with our notes. Okay, so a special type of polynomial function is called a power function. And it is of the form f of x equals a x to the n. And notice there's no other terms. It's simply x to some exponent with a coefficient out in front. N still has to be a positive, non-negative integer, so positive, where a is a real number and a is not equal to 0. Because if this was 0, just 0 times something is 0. And n is a positive integer. Okay, we can go with that. And there's some special properties now of these power functions that we are going to be utilizing through this unit. So if n is even, and remember n is just the exponent here, then the function is even. Remember, we found this out in our last unit. This means you had symmetry about the y-axis, meaning it's symmetric with the y-axis. If n is odd, then the function is odd. And again, we found this in our last unit. Functions are odd if they're symmetric with regards to the origin. Okay, so now as n increases, so as the power, the exponent gets larger, the graph increases more rapidly. So for x values near the origin, the graph tends to flatten out and lies closer to the x-axis. So grab a calculator if you don't have one handy, and we're going to take a look at some of these. So for example, if I were to go into y equals, and let's just put x raised to the 4th power. Let's take a look at that graph. It looks similar to a quadratic, doesn't it? Which is just x to the squared power. What if let's put in another one in y2. Let's do x raised to the, let's do a much higher power. Let's do the 10th power, how about? So again, it's still an even exponent. And look at the graph. Let's compare these. And so notice the red lines is x to the 10th. It rises much faster or more rapidly than x to the 4th, and it's flatter when you get close to x equals 0. If I were to plug in something x to, let's say, the 100th power, it's going to get even flatter and rise up much faster. Okay, but let's take a look now. Come back here and clear my calculator. We're going to graph a couple of these. So 1 minus x to the 5th. Let's put that in the calculator. 1 minus x raised to the 5th power. So first of all, this is going to be an odd function because it is raised to an odd power. And the x has been reflected vertically, and we've gone up by 1. So if we put this in the calculator and graph it, here's what our function does. And let's go ahead and graph this. And I'm going to say that these represent 0.25. So you need to go 4 over to get 1. 4, just so that we have some space to graph here. 1, 2. Oops, that should be right there. Okay, and 1, 2, 3, 4. 2, 3, 4. So fairly accurately here, this is going to be at 0, 1. This is going to be 1, 2, 3, 4. And if you check your calculator for these values, you'll see that it looks something like this. Similar to what our cubic function does. So it should look familiar. Now let's take a look at, this is called a quartic because it's to the 4th power. Again, let's put this in the calculator, clear out that old one. So 1 divided by 2, parentheses, x minus 1, raised to the 4th power. And we'll take a look at our graph. And notice that the calculator is a bit slower when it graphs these. It's got to think about it. So if we were to go ahead and graph this now, we know that we've got a vertical compression by 1/2, and it's gone right 1. So again, I'm going to count off by 4s. 1, 2, 3, 4. And let's get this graph. So the origin has moved over from here to here. And 1, 2, 3, 4. And that's only gone up to here.